Hello everyone. We ended up with this problem concerning bulk modulus of elasticity. So we now proceed with our next topic. So we have pressure inside a droplet of liquid. Okay. So this is a continuation of surface tension. No, I have already introduced surface tension. No. So this time let us analyze a droplet of liquid. So as you can see in the figure, we have a droplet, droplet of liquid. And what is happening to the liquid? It forms a sphere, right? It is it forms a sphere, and in this case, no, that is due to cohesion. No, there are cohesive forces or intermolecular forces, no, existing, no, between molecules, no. So there are cohesive forces, okay? So attracting each other. And doing that, they form this figure which is a sphere, no? Okay, so let us analyze the given figure. Suppose we are interested in finding the pressure inside this sphere of liquid, no? Spherical liquid, no? Okay, so let's consider this figure now. So we have here a sphere of water, of liquid, no? And cutting it into half, no? So there is pressure inside this droplet, no? And we are interested now in finding that pressure inside the droplet. So to find that pressure, let us derive the formula. So we cut it in half and we apply a force, no? So there is a force that exists due to pressure inside this uh, inside this droplet, no? And the formula for that is the product of the pressure inside and the area will give us that force, no? Okay, so will give us that force, no, corresponding force. No, we consider this area, so it has diameter, of course, and in that case this area is considered, no, so there is pressure that exists in this area, and that pressure, when we multiply it by that area, we get that force. Okay, now that force is resisted, no, by these tiny forces, no. So this is due to surface tension, no. So there are differential forces, no. So differential forces that exist that resist this force due to the pressure, no. So so these are the differentials of the force, no. So we will sum up all of those, no, summing up all of those differentials. Okay, when I talk about differential, I'm referring to an infinitesimal quantity, no, infinitesimal amount of force. Okay, so adding all of those infinitesimal amounts, I will then integrate, no, so that I can get the total force. Okay, that resists this force due to the pressure, no? So we will sum up forces, no, along vertical equal to 0. So we'll apply here Newton's first law of motion. Okay? So applying Newton's first law of motion, because in this case the there is equilibrium, right? So there's no motion. So there is equilibrium, okay? And if the body is in equilibrium, Newton's first law is can be applied, no? Newton's first law can be applied. With that, we have now this equation. So summing up all of these differentials, no? To sum up all of these differentials, I will integrate, no? So integrating dfs sub t. So this is due to surface tension, no? So integral of dfst, then minus the force acting downward, no? So that is the product of pressure and the area. So that is now equal to 0, no? That is now equal to 0. So take note that it is the same, no? There is also force acting upward. So there is force acting upward, okay, equals to PA, no? With the same magnitude but opposite in direction, okay? And there is differential forces due to surface tension, okay? Differential forces that exist, no? So differential forces due to surface tension, okay? So with that, we shall continue. So when we integrate the fst, no, we get F sub st, the force due to surface tension, no. So there is surface tension, no. So and with that, we equate the surface tension force to the product of pressure and area, no. And with that, we have now uh, so we expound, we have F sub st, no, the formula for surface tension. So the coefficient of surface tension, or simply surface tension, we know the formula, it's force over the length, right? The force over the length, okay? And with that, F now, so that is the force due to surface tension, okay? The force due to surface tension is now equal to the product of the two, okay? The coefficient of surface tension times the length. So that's why we have this, okay? Then we divide it by the area, so we will obtain now the pressure, okay? So with that, the length that we will consider here is the circumference of the circle, no? Where differential forces due to surface tension exist, no? So with that, we have the surface tension and the circumference. So the length of this circle is the circumference of the circle, no? And the circumference is simply pi d, no? Pi multiplied by the diameter of the circle. And then we divide by the area, wherein the area is perpendicular to the force, no? So the area, so since it is a circle, the area is in terms of diameter, that is pi d squared over 4. Okay, and then we have now this equation. Okay, so cancel. Okay, so cancel. Okay, then we have now sigma st d over 1/4 d squared. So 1/4, so this will become, so the reciprocal of 1/4 is 4. No? Then by loss of exponents, d over d squared, so we have now d in the denominator. That's why we have this formula. Okay? So 4 sigma st over d. Okay? So that's the formula on how to calculate the pressure inside a droplet of liquid. No? Now, so we proceed with the problem. No? So what is the value of the surface tension of a small drop of water, 0.3 millimeter in diameter, which is in contact with air if the pressure within the droplet is 561 Pascal? So required is the surface tension of a small drop of water. So if this is the small drop of water and having a diameter of 0.3 millimeter, okay, so it is in contact with air. Now, so we have the water and air in its surrounding. No? So the pressure inside this droplet now is 561 Pascal. Okay, so 561 Pascal. And take note of the direction of the pressure. The pressure is uniform. No? The pressure acts outward. Okay, the pressure acts outward. Okay, so that's the direction of the pressure inside. Okay, so if there's no surface tension, it will burst, right? Okay, this will burst. Okay, so madideform ito, hindi siya spherical kung walang pumipigil sa pressure. Okay, so then solution. The pressure formula for sigma st over d. So we have now sigma st. Okay, the coefficient of surface tension is simply PD over 4. And we have 561 Pascal for the pressure. The diameter of the droplet is 0.3 millimeter. When we divide it by 4, then we divide it by 4. And take note the conversion for every Pascal, that is 1 Newton per square meter. So this will be eliminated, right? And also, take note, we have millimeter. So milli means 10 to the negative 3. So if this is if this is 10 to the negative 3 meter, so if the unit is meter, this will become, if this is meter, so this will become millimeter. So milli, it means 10 to the negative 3. So with that, we have this one. So for every millimeter, 10 to the negative, we have 10 to the negative 3 meter. Now for every millimeter, so 1 millimeter is 10 to the negative 3 meter. No? So that we can able to cancel. No? This will be cancelled out. Okay? And what unit is left? Okay? This one and this one. We will multiply. So Newton per square meter. Okay? So we have Newton per square meter multiplied by meter. Okay. Then we divide it by, so nothing, no unit left. So that will be 1. So we have now Newton per meter over 1, or simply Newton per meter. No? So that is simply Newton per meter. Okay? So that's it. So that's the unit of surface tension. Newton per meter is force over length, right? So we have 0.0421 Newton per meter. So we proceed. So let's now proceed with our next property of fluid. Next property is called viscosity. So what is viscosity? It is a property of a liquid, okay, by virtue of cohesion and interaction between liquid molecules of a resistance to flow. Actually, it's not only liquid, it can also be gas, no? So fluid in general, okay? Because gases, we can also, this is also applicable to gases, okay? So it's a property of a fluid by virtue of cohesion, okay? So by virtue of cohesion and interaction between fluid molecules offers resistance to flow. So have you noticed that this is let's say this is water, and as you notice, when it flows, it easily flows, right? Compared to oil, or even let's say honey, no? Compared to honey. If this is honey, uh, it's easy for water no, to come out of the container compared to the other substances, which is oil and honey. Okay? Okay. So comparing the liquids as shown, no? So there is now resistance to flow, no? Resistance to flow of the fluids, no? The three fluids. Okay? But we can able to say that one has a higher viscosity than the other, no? Since comparing the viscosities of the three, we can say that this has the highest viscosity, no? This has the highest viscosity, which is honey, because uh, there is more resistance to flow than water and oil, no? There is more resistance to oil, okay? And we can say that water has the least viscosity, no? Siya yung may pinaka malit yung value na viscosity dahil uh, madali siyang mag-flow, okay? So yun ang property ng liquid, no? uh, because of cohesion and interaction between fluid molecules. Okay? So, cohesion, pag sinabi natin cohesion, attraction between two molecules or between two substances, between two like substances or between two like molecules, no? Or two like particles. Okay? So, yun ang viscosity. So, another definition is a measure of a fluid's resistance to flow arising due to the internal friction between the fluid layers. No? So, internal friction. Okay? Di ba kapag yung halimbawa, meron kang halimbawa na lang, meron kang pinupush na bagay. No? Kung ang sahig ay magaspang, rough, sabihin niyan, greater ang friction. Diba? Kaya kung smooth, mas madali siyang i-push. Diba? Mas madaling i-push yung bagay na to. Okay? Kasi smooth ang surface ng floor. Ito rough. Okay? Ito rough. So kapag rough, sabihin na mas mataas yung friction, no? Friction force. So yung force na yan na ina-apply mo, may kumokontra, no? Which is frictional force, no? May kumokontra frictional force. Okay? So may kumokontra sa direction ng force mo. Unlike pag smooth, kung may kumokontra man sa direction ng force, maliit lang ang value kumpara doon sa rough yung surface. No? So, ganun siya. Alright? Fluids with high viscosity, such as syrup, deforms relatively more slowly than viscosity of fluid, such as water. So, if we compare the three, no? So, let's say this is honey, no? So, deforms relatively more slowly, no? So, deforms somewhat more slowly, right? So, deforms relatively or deforms somewhat more slowly than viscosity of fluids such as water. Okay? So, mas mabagal ma-deform. Ito. Okay? So, itong syrup na honey, no? Kumpara sa tubig. Mabagal ma-deform. Okay? Okay. So, we can now proceed. So, suppose we have a fixed plate, okay, and a movable plate, and there is steel between the two plates, okay, and in this case, uh, the fixed plate is rigidly fastened in the steel plate, in the steel, no? So, and since this is movable plate, if we if there's no force applied, so this will be the outcome. There's no force applied. However, if we apply a force to it, since it is movable, now greater than 0, and we know that the movable plate is attached to the steel plate. Therefore, if the force is greater than 0, there's a certain amount of deformation. Okay? There's a certain amount of deformation. Okay? So that deformation is this one. So, this one is deformation. Okay. So we form a triangle here. Okay. All right. So there is now deformation, no? And that deformation can be measured. So this is the deformation of the object. Okay, so there's deformation. So, and we consider this as, no, the length. Okay, and we have an angle here. We can call it as angle gamma. Okay, and tangent gamma is simply equal to, opposite is delta, no, over L. Okay, so alam na natin yung SOHCAHTOA, right? So tangent is opposite over adjacent. So opposite over adjacent. And tangent gamma is very, very small. No, that is approximately equal to gamma. So that's why gamma now, okay, is equals to delta over L. And we call gamma as strain, shear strain. Okay, we call gamma as shear strain. Okay, all right, so we continue. And we call delta here as shear deformation. Okay, you know what shear is, right? So this is a shear force. No, this is a shear force. So as you notice, what area is affected here? What area? Actually, meron niyang thickness, right? Meron niyang thickness yung plate, yung movable plate. No? So let me illustrate. So meron kasi itong thickness. Okay, meron itong thickness. Sorry, medyo I'm struggling. Okay. Ayan, meron yung thickness. So, tapos, doon, nag-act yung force. Pero, sa ilalim, naapektuhan. No? Actually, meron pa yan eh. Meron ding ilalim yung sa steel na yan. Yung part na to, na para, yung area sa part na to, okay, naapektuhan yan dito. Yung area dyan sa ilalim. So, ang force ay parallel sa area. Okay? So, ang tawag natin ngayon sa force na yan ay shear force. Shear force. At meron ngayong shear stress. So, meron tayong shear stress dito sa ilalim ng plate na yan. Okay? Sa ilalim ng plate na yan. So, actually, di naman talaga yun yung lesson natin, pero may connection ito sa ating topic. No? So, ito ay lessons sa strength of materials. Okay. So, let's now proceed, no? Okay? So, baka naguluhan kayo. Actually, pag kukumpletuhin natin yan, ganyan yan eh. Okay? Pasensya na sa drawing. Ayan, okay. So, kumbaga, nag-apply ka ng force. Yung partly dito, Tapos may area dyan, yung cross-section area dyan. Okay, yun yung affected. Okay? So, with that, nagkakaroon ngayon ng shearing stress sa ilalim ng movable plate. No, yung interface ng movable plate and yung steel. Sa interface niya, merong shear stress na nagdudulot ng no, shear strain kapag nagkaroon ng deformation. Okay? So, let's consider two large parallel plates at a small distance y apart. Okay? The space between them being filled with a fluid. So, consider two large parallel plates. So, meron tayong fixed plate, and meron tayong movable plate, and then, at a small distance y apart, no? Ito siya. So, the space between them being filled with a fluid. So, ito siya. Fluid. Okay? Like water, no? Now, consider the upper plate to be subjected to a force. So, isa-subject natin siya sa force. So as to move with constant velocity u. So as to move with constant velocity u. Okay? So, ibig sabihin yan, pag nag-apply tayo ng force, dahil ito ay movable plate, magkakaroon siya ng speed. Right? Ang speed na yon ay constant. Okay? So, assuming constant, no? Assuming constant speed. So, in that case, pag nag-apply tayo ng force, magkakaroon ng speed u, which is considered constant. Okay? At yung interface ng fluid at yung movable plate, no, yung pagitan ng dalawa, ay yung affected area. No, sa pagitan ng dalawa, yung interface, may affected area yun sa area dito. Sa interface ng fluid and movable plate. So, nagkakaroon ng shearing stress. No? Nagkakaroon ngayon ng shearing stress dahil ang force na yon ay parallel sa area. Pag ang force ay parallel sa area, ang tawag natin ay shearing stress. Okay? Now, so the upper plate is subjected to a force F so as to move with a constant velocity u. The fluid in contact with the upper plate will adhere to it. No? Aayon siya. The fluid in contact with the upper plate will adhere to it. No? So, sabihin, di siya sasalungat. Aayon. Will adhere to it and will move with the same velocity u. Okay, kung ano yung bilis ng plate, yun din yung bilis ng mga molecules ng fluid na nasa interface. Okay? So, the fluid in contact with the upper plate will adhere to it and will move with the same velocity u, while the fluid in contact with the fixed plate will have zero velocity. So, kung ano yung bilis ng movable plate sa taas, yun din ang bilis ng tubig, ng fluid sa interface ng movable plate at fluid. Pero, sa ilalim, zero. Sabihin, walang paggalaw ng fluid na nasa ilalim. Okay? Yung interface ng fixed plate at fluid. Yung sa pagitan ng dalawa. Walang paggalaw ng tubig. Ng fluid. Okay? So, kung ganon, dito may paggalaw, sa ilalim wala. Okay? Dito sa itaas may paggalaw, sa ilalim wala. Which is valid naman, right? Kasi kung kung nagbabangka ka, no? meron kayong bangka, tapos nagsasagwan kayo. So, gumagalaw din ba, naapektuhan ba yung pagsagwan mo sa paggalaw ng fluid sa ilalim nun? Let's say, yun ay, let's say, 1 meter. Not, hindi siya, not considerable, not appreciable, di ba? Okay, almost zero. Kung may paggalaw man, almost zero. Okay? So, the fluid in contact with the upper plate will adhere to it and will move with the same velocity u, while the fluid in contact with the fixed plate will have zero velocity. So, we continue. So, consider natin ito. Let's say, itong line na to, okay, papunta dun sa fixed plate. So, sa ilalim, zero ang speed, no? So, meron tayong movable plate, meron tayong fixed plate. Sa ilalim, zero ang speed. So, for small values of u and y, we have the velocity gradient, no? That can be assumed to be a straight line. Okay? That can be assumed to be a straight line. So, yung u and y natin, maliit lang ang value niyan, no? For small values of u and y, the velocity gradient can be assumed to be a straight line. Ito siya. Ito yung velocity gradient na tinutukoy niya. Okay? Ito. Ito yung velocity gradient na tinutukoy niya. Okay? So, the velocity gradient can be assumed to be a straight line. Okay? And F varies, no? As A, U, and Y, no? As F proportional to A, U over Y, no? Okay. So, pansinin natin, when we talk about velocity gradient, we're pertaining to the slope ng velocity. Okay? So, in that case, ito siya. It is assumed to be a straight line. And F varies as A, U, and Y as F proportional to A, U over Y. So, sabihin niyan, okay, so upon performing experiments, okay, the force, no, applied to the movable plate is directly proportional to the area, ano, itong area na nandito, no, sa part na tinatamaan, ito, yung area dyan, okay, yung area sa part na tinatamaan. So, and F varies as A, U, so sabihin niyan, pati yung velocity, no, nagdidepende daw yung force, no, sa area, okay, sa interface ng fluid and movable plate, sa velocity ng fluid na katulad ng velocity ng movable plate na constant, at nagdidepende din sa distance ng dalawang plate, no? So, ito siya, y. Nagdidepende din siya. Okay? So, sabihin yan, pag mataas yung y mo, mababa yung f mo. So, inversely proportional. Directly proportional to A and U. Inversely proportional to y. no? Okay, so we proceed, no? So, in this case, let this be V, no? So, meron tayong velocity sa taas, which is U, okay? At maglagay tayo ng uh, horizontal strip, okay? Mag-apply tayo ng calculus. So, maglagay tayo ng horizontal strip at itong strip na yan, okay, has something to do with velocity. So, ibig sabihin niyan, ang velocity u natin, habang pailalim ng pailalim, bumabagal. Okay, hanggang maging zero. Okay? Pinakamabilis sa taas, habang palalim ng palalim, nababawasan. No? With respect to yung distance. Di ba? Yung vertical distance, nababawasan. Okay? Hanggang maging zero. Okay. So, with that, so, yung isang strip na yon ng velocity represented by this. Okay? So, meron tayong differential y, which is an infinitesimal value. So, meron tayong velocity, okay, with what we call as a differential part of the velocity, no? Kasi pag naglagay tayo ng horizontal strip, may part na hindi makukuha, di ba? So, sabihin niyan, itong area na to hindi nakuha. Okay, may part na hindi nakuha. Yun. So, yung part na hindi nakuha na yon, no? So, may mga elements involved doon. So, yung dito niya, kung ito yung velocity natin, okay, velocity ng strip na to na horizontal, okay, meron karagdagan na velocity, which is an infinitesimal value. So, meron kang v dv, no? So, v dv. So, going back, since the force is proportional to A, U, and Y, and inversely proportional to Y, so, yung alpha na yan, which is a proportionality symbol, can be represented by mu, the Greek letter mu. Okay? So, that is a constant value, mu. And, ang tawag ngayon natin sa mu na yan ay absolute viscosity. Absolute or dynamic viscosity. Yan ay isang constant. No? Constant sa isang fluid. Absolute or dynamic viscosity. No? So, with that, no, ayusin natin yan. F over A equals to mu U over Y. So, ang F over A ay shear stress. No, dahil ang area natin, yung area dito, okay, sa pagitan ng fluid at movable plate, yung interface, ang force ay parallel sa area. So, therefore, it is denoted by the Greek letter tau, which is shearing stress. No? So, Greek letter tau. Okay? Now, consider this. We have y, we have u, okay? So, meron kang y, meron kang u. So, meron kang triangle ngayon. Okay, y and u. So, meron ka ring para dito, dv, dy, ito dy, no? Ayan, meron kang dv and dy. So, by similar triangles, no? So, since meron silang parehong angle, no? Pareho yung kanilang angle. Okay? Pareho yung kanilang angle. So, tangent gamma equals to u over y. Tangent gamma equals to dv over dy. So, kasi pareho yung kanilang angle dito, similar triangles sila, no? So, similar triangles. Dito, tsaka yung doon niya ay equal. Okay? So, sa geometry, naaral nyo yan, no? So, with that, we can proceed. So, we can therefore say that u over y can now be represented by dv over dy, no? It can now be represented by dv over dy. So, therefore, the absolute or dynamic viscosity can be solved by dividing the shear stress to dv over dy. So, anong tawag natin sa dv over dy? So, ang tawag natin dyan ay, so, mu ay absolute or dynamic viscosity. Ang tau ay shearing stress. Ang dv over dy ay rate of shear strain. Okay? Rate of shear strain. Paano siya naging rate of shear strain? Di ba nasabi ko sa inyo yung kanina? Yung example ko kanina doon sa naunang drawing ko. Okay? So, yung tangent gamma equals delta over L. Okay? So, yung delta na yan, anong unit? Ang unit niyan ay, so, unit of length. Yung delta na yan. Okay? So, ang L na yan ay unit of length din. Okay? So, ang angle ngayon natin ay in radian or degree. Okay? In radian or in degree. Similarly, ang U natin ay speed over distance. So, kung meron kang angle dito, okay, speed over distance. So, U over Y. So, sabihin natin ang U ay nakameter per second. Ang Y ay nakameter. Meter per second over meter. Cancel. Ano matitira? Meron siyang per second. Per second. Radian per second. Okay? Matitira nun radian per second. Okay? So, yung radian per second, sabihin, nagbabago yung angle dito with respect to time. Kasi, nagbabago yung speed nagbabago kasi yung speed dito eh. No? Habang pailalim ka, nagbabago yung speed. No? Habang pailalim ka. Okay? So, tapos, nagbabago din yung angulo dito with respect to time. Dahil, papunta dun eh. Okay? Papunta sa ganitong direksyon yung speed. So, nagbabago yung angulo with respect to time. So, kaya, rate ang tawag. No? Rate. So, shear strain, kasi ang gamma na to ay strain. Shear strain yan. Tapos rate, kasi nagdi-depend sa time. No? Nagdi-depend sa time. Okay? Anong unit ng dV? Meter per second, halimbawa. dy, meter. So, nagdi-depend sa time. Kaya rate of shear strain. Okay, U is the constant speed of the movable plate. So, let's now proceed with kinematic viscosity. For kinematic viscosity, it is the ratio of dynamic viscosity to density. So, yan ang formula. Denoted by the Greek letter nu. Okay, ito ay Greek letter mu. Ito ay Greek letter rho. Okay? Ang tawag natin dito ay absolute or dynamic viscosity. Ang tawag naman natin dito ay density. Ang tawag natin ngayon dyan ay kinematic viscosity. Ayan. Okay? So, ratio lang yan ang dynamic viscosity sa density. Setting mga common units of viscosity. Okay? Meron kang absolute or dynamic viscosity. Meron kang kinematic viscosity. So, the Greek letter mu for absolute or dynamic. The Greek letter nu for kinematic. So, tapos, recall natin yung sa part 1 of your module na diniscuss ko. So, pag viscosity, okay, pag dynamic, okay, pag meron tayong FLT system, force, length, and time. No? Force, length, and time dimension. Okay? So, ano magiging unit niya? FL negative 2T. No? Check nga natin. Pound second per square foot. Ano ang pound? Force. Ano ang second? Time. Tapos meron siyang per square foot. Ano yung foot squared? Length squared. Kaya F, L negative 2, bring up T. Okay, FL negative 2, T. No? So, yan ang unit ng absolute viscosity. Or, pwede rin siyang mass, length, and time system. MLT. Ito siya. Okay? Kung MLT, analyze natin. Slug, mass yan, over feet second. Ano ang feet? Length. Ano ang second? Time. No? So, we have now M, L negative 1, T negative 1. M, L negative 1, T negative 1. Okay? Okay. O, pag metric system or CGS, by the way, ang English ay yun din yung BG, yung British Gravitational System, no? Tapos meron akong introduce na bago, yung metric system or CGS system, no? Centimeter, gram, second system. Centimeter, gram, second system. So sabihin yan, CGS. So kung CGS, ang force represented by dyne, ang time represented by second, ang length represented by centimeter. Okay? So, sabihin niyan, dyne second, square centimeter. Okay? Or, isa pang unit niyan ay poise. No? Poise. Metric system. Para sa absolute or dynamic viscosity. Okay? So, mamaya, meron niyang equivalent ilang poise meron sa dyne second per square centimeter. So, I'll discuss that later. For SI, we have Pascal second, no? So, Pascal second or Newton second per square meter, no? Pascal second or Newton second per square meter. And then, ating mga conversion, for every poise, 1 dyne second per square centimeter or 0.1 Pascal second. Okay? 1 poise is 0.1 Pascal second. 1 Pascal second, 1 Newton second per square meter. I'm encouraging you to memorize, no? 1 Pascal second, 1 kilogram per meter second, 1 pound second per square foot. That is 1 slug per foot second. So, equivalent nito, ito. Okay? And then, 1 dyne, that is 10 to the negative 5 Newton. So, ibig sabihin yan, ang 10 to the negative 5, so ibig sabihin yan, pwede kong baliktarin. 1 Newton is 10 to the 5 dynes. No? Ang 10 to the 5, 100,000. 1 Newton is equals to 100,000 dynes. No? Or, tapos meron ka dito, 1 pound, 4.448 Newton. No? 1 pound, 444,800 dynes. Okay? 1 slab, 1 pound second squared per foot. No? O tapos, punta naman tayo sa kinematic viscosity. So, meron ka ditong kinematic viscosity. Okay? Anong unit ng feet? So, feet squared, so that is length. So, meron kang L squared length over time. Or simply, L squared T negative 1. Okay? So, yan siya. L squared T negative 1. Pareho sila, FLT, MLT. Kasi wala namang mass and force. Kaya pareho sila. No? And then, for metric system or CGS, so meron tayong square centimeter per second. No? Square centimeter per second. Or Stoke. Okay? Pwede rin siyang Stoke. No? So, take note, ang 1 square centimeter per second ay 1 Stoke. No? Or 1 Stoke is equals to 1 square centimeter per second. For SI, ang kinematic viscosity, naka-express siya in square meter per second. No? So, let's take note lang, characteristics of fluid, no? Of fluid viscosity. So, viscosity of a liquid decreases with temperature increase. In short, if there is an increase in temperature, no, there will be a decrease in the viscosity of the liquid. No? Okay? So, napansin nyo ba, pagka tawag dito, meron kayong, yung ano na lang, milk na lang, milk. Okay? Tapos, painitin mo sa kalan, yung milk. Okay? Siyempre, yung milk ilagay mo muna sa saan tawag dito? Lalagyan. Let's say, sa isang container na kung saan yung container ay pangluto. Okay? Ilagay mo doon. So, tapos, pakuluan mo. So, nandito yung milk. Okay? I-compare mo. Halimbawa, naka-ref yung milk. I-compare mo kung naka-ref yung milk. No? So, mula nasa ref, hindi naman naka-freezer, nasa ref lang. Okay? Tapos, experiment mo, yung milk na yan ay ilagay mo sa isang baso. Lagay mo na malamig yung milk, no? Malamig yung milk. Pag nilagay mo yon, papansin mo, ba't ang bagal mag-move ng milk? Pero pag pinakuluan mo yung milk, bakit ang bilis malagay sa baso ng milk? Kasi yung kanyang viscosity ay bumaba nung pinainit, no? So viscosity of a liquid decreases with temperature increase, no? With temperature increase. Madaling malagay ngayon sa baso yung milk pagka pinakuluan kumpara sa milk na nasa ref, no? Hindi madaling nilagay sa baso. Hindi ganun kadali. Mas mabilis malagay sa baso yung mainit na milk kaysa sa malamig na milk. Dahil yun sa property of liquid na viscosity. Pero, sa kabilang banda, viscosity of a gas increases with increase in temperature. O pag gas na pinag-usapan, baligtad na nangyayari. No? Pag nag-increase ang temperature, mag-increase yung viscosity ng gas. No? Mag-increase yung viscosity ng gas pag nag-increase yung temperature. Okay? So, baliktaran sila. Para sa liquid, an increase in temperature results to a decrease in viscosity, whereas an increase in temperature will result to an increase in viscosity of gas also. No? So, ganun siya. Increase in gas viscosity. Okay, when there is an increase in temperature. So, let's answer a problem. If the viscosity of water at 70 degree Fahrenheit is 0.00402 poise and its specific gravity is 0.978, determine its absolute viscosity in Pascal second and its kinematic viscosity in square meter per second and in Stoke. So given. So the density of water at 70 degree Fahrenheit is 0.00402 poise. The specific gravity of water at 70 degree Fahrenheit is 0.978. Required are as follows. The absolute viscosity of water at 70 degree Fahrenheit expressed in Pascal second. Okay, SI unit, Pascal second. And its kinematic viscosity in square meter per second, SI unit, and in Stoke. Ang Stoke ay ano din yan, CGS. CGS unit yung Stoke. Okay? Na-introduce ko ba yan, yung Stoke? Tignan natin yung Stoke. Stoke. Ayun, 1 Stoke is 1 square centimeter per second. No? Okay. Solution. So the density of water at 70 degree Fahrenheit is 0.00402 poise. We will express the absolute viscosity, of water at 70 degree Fahrenheit is equals to 0.00402 poise. And we are to convert this to Pascal second. No? So, take note of the conversion. For every poise, 0.1 Pascal second. So, we will obtain an answer of 4.02 times 10 to the negative 4 Pascal second. And then, for the kinematic viscosity of water, So we divide the density of the liquid to, we divide the absolute viscosity of the liquid to the density of the liquid, no? So, which is a temperature of 70 degree Fahrenheit. With that, something we should consider is the density of water at 70. So, the standard density of water is at 39.2 degree Fahrenheit. That is at 4 degrees Celsius. 4 degrees Celsius or 39.2 degree Fahrenheit. No? And the density of water at that temperature standard is 1,000 kilogram per cubic meter. No? That is at a temperature of 4 degrees Celsius or 39.2 degree Fahrenheit. Okay? Ngayon, recall natin on how to calculate the specific gravity of a substance. So, ang specific gravity ng isang substance, okay, ay equal yan sa density ng substance over density ng water at 4 degrees Celsius. Ito yung standard, no? Yung water at 4 degrees Celsius or 39.2 degree Fahrenheit. Okay? So, therefore, yung specific gravity ng substance, i-multiply natin sa density ng water at 4 degrees Celsius. Yan yung density ng substance at a certain temperature. No? Yan ang density ng substance at a certain temperature. Kaya minultiply natin. No? The specific gravity of water, ito yon at 70 degree Fahrenheit. I-multiply mo sa density of water at 39.2 degree Fahrenheit. Na-equal yun dito. Density of water at 70 degree Fahrenheit. No? Alright, so going back. So this is 4.02 times 10 to the negative 4 Pascal second. Ito yung given, no? And the specific gravity ng water is 0.978. Ito yung given sa problem. Density of water at 39.2 is 1,000 kg per cubic meter. So, i-convert natin. For 1 Pascal, 1 Newton per square meter, cancel. No? Then, 1 Newton, cancel yon. 1 kilogram meter per second squared. So, kilogram, cancel. So, anong matitira? Second, merong 1 over square meter. Meter per second squared over 1 over cubic meter. Okay. So, ano magiging final unit niyan? So, second squared. So, second na lang. Meter squared, meter na lang. So, matitira 1 over meter times second. Ito, 1 over meter cube. So, yung 1 over meter cube magiging meter cube over meter times second. Okay, tataas siya by loss of fraction. So, magiging square meter per second. Yun ang unit. Square meter per second. 4.11 times 10 to the negative 7 square meter per second. So, knowing that, i-convert daw natin siya ng Stoke. No? I-convert natin siya ng Stoke. So, para ma-convert natin siya ng Stoke, recall that 1 Stoke is equals to 1 square centimeter per second. Okay? So, recall natin, no? Itong table, okay? Ang centi 10 to the negative 2. Kaya, kung centimeter yan, centimeter, At pag in-square ko yung centimeter, may square din ito. 10 to the negative 2 meter square. In-square ko yung centimeter eh. So, ano yung 10 to the negative 2 square? 10 to the negative 4 square meter. Ayan. Negative 2 times 2, negative 4. 10 to the negative 4 square meter. Therefore, 1 square centimeter is equals to 10 to the negative 4 square meter. Doon nakuha yan. Okay? And then, we'll get an answer of 4.11 times 10 to the negative 3 square meter per second. And that is stoke. No? 1 square centimeter per second is 1 stoke. So number 2. So from the International Critical Table, the viscosity of water at 20 degrees Celsius or 68 degrees Fahrenheit is 1.008 centipoise. Compute the absolute viscosity in pounds second per square foot. Letter B, if the specific gravity of water at 20 degrees Celsius is 0.998, compute the kinematic viscosity in feet square per second. Solution, letter A, so we're looking, so density of water at 20 degrees Celsius, no, is 1.008 centipoise. So this is 1.008 centipoise, no? So 1.008 centipoise ito. Okay? So i-multiply lang natin for every centipoise 10 to the negative 2 poise kasi centi 10 to the negative 2, di ba? Okay? So and then for every poise 1 second per square centimeter. Okay, 1 second per square centimeter for every poise. Tapos, for every dyne, 1 pound. So for every dyne, or should I say, for every pound, 444,800 dynes. I'm encouraging you to memorize nyo, no? Yung mga ito, conversion, no? 1 pound is 444,800 dynes. Ano bang goal natin? Makuha natin yung absolute viscosity in pounds squared, pound second per square foot. No? Check natin. Cancel. 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 Ano natira? Pound second per square centimeter. May kulang pa. No? Pound second per square centimeter. So, cancel na yan. So, ating conversion. No? So, para ma-cancel yung square centimeter. So, alam natin yung 1 foot ay 30.48 centimeter. O, remember yan, na 1 foot is 30.48 centimeter. So, memorize nyo. So, pag in-square ko yan, 30.48 centimeter square, ang result ay 30.48 square centimeter. So 30 may square yung number. So magiging 30.48 square centimeter. Kaya 1 foot squared equals to 30.48 square centimeter. Yun ang purpose nun. Okay? So tingnan natin ngayon yung ating problem. So cancel. So, meron kang pound second per square centimeter. Ito. Times. Meron ka ditong square centimeter, tsaka feet squared. Ayan, cancel. So, pound second per square foot. Yun ang unit. Cancel na ninyo yung square centimeter. Okay? Pound second. Okay? Pound second per square foot. Yun ang unit. Yun ang lilitaw na unit. Yun ang hinahanap natin. Pound second per square foot. No? So, pound second per square foot. Okay? So, 2.105 times 10 to the negative 5 pound second per square foot. O, letter B. So, the specific gravity of water at 20 degrees Celsius is 0.998. No? Find the kinematic viscosity in square foot per second. No? So, ang required ay kinematic viscosity in square foot per second. So, alam natin that kinematic viscosity is equals to absolute viscosity over density. So, that is, this is our reference temperature. So, this is density of water at 20 degrees Celsius. So, ang gagawin lang natin para makuha yan, we will multiply the specific gravity of water at 20 degrees Celsius by the standard density, which is at 4 degrees Celsius. No? So, ganun lagi. Okay? Specific gravity times yung standard temperature. Sorry, standard density at a certain temperature. No? Okay. So, we continue. Okay, so yan ang hinahanap, no? So, with that, we have now, so ito yung nakuha kanina, the absolute viscosity of water at 20 degrees Celsius, 2.0105 times 10 to the negative 5 pound second per square foot, no? Ito rin yung given kanina, 0.998, no? Then, density of water at 4 degrees Celsius. Ito yung common, ito yung standard, 1.94 slug per cubic foot. No? So, and then, ano magiging final unit? So, ang slug ay express natin in terms of pound. That is 1 pound second squared per foot. No? Memorize nyo. No? Kaya, naging ganyan siya kasi ang isang slug ay 1 pound second squared per foot. Para makancel yung slug. Kasi ang goal natin ay magkaroon ng unit na feet square per second. No? Square foot per second. Diba? Yun ang goal natin. Square foot per second na viscosity, kinematic viscosity. Okay? Kaya dapat mawala yung slug. Pag nawala yan, makakancel yung pound. So, ano magiging unit? Second per square foot times 1 over 1 over foot. Kasi, meron pa palang second squared doon. So, matitira dito ay 1 over second squared per foot. Dito, second per square foot over, meron pa siya dito, over second per square foot over 1 over cubic foot, yan, times 1 over second squared per foot. Ayan. So, simplify. Pag sinimplify natin, uh, magiging ano lang. So, meron kang feet squared tsaka feet cube. Magiging feet na lang. Okay? So, tapos 1 over foot second. So, pag sinimplify yan, mapupunta sa taas yan. Okay? 1 over, reciprocal ng 1 over foot is foot. So, magiging foot second. Foot times second. Diba? Times. Reciprocal ng 1 over second squared over foot. Feet per second squared. No? So, ang feet, foot, foot squared. Second squared, second na lang. So, foot squared per second. So, that is our goal. Tama. No? So, 1.087 times 10 to the negative 5 square foot per second. No? So, that ends my presentation. So, I hope you get it, class. No? So, good day, everyone.